I clicked buttons.
You shouldn't do that.
Back to meeting. Screen. How do I? Oh, I just went over to Zoom accidentally.
All right.
I was trying to hide it, but
All right.
I don't know if I can hide it. It just keeps going like.
Just, it's okay. No, I don't mind seeing the little thing in the corner that it shows us.
All right.
Oh, and also you might want to speak into the mic for some people.
All right. So for our next talk, we'll hear Deborah Ferguson from UIUC, where I got my PhD, and where all good people come from. So she's going to tell us about obtaining accurate waveforms with Cauchy characteristic evolutions, and maybe you want to say something even about getting a thorn into the Einstein Toolkit.
Oh yeah, I can talk a little bit about that. Not as painful as one would think. All right, is that good? Can everybody hear me? Good. Great. All right. Oh, I walk too much, so this is going to have to go in a pocket. Okay, all right, so today I want to talk to you guys a little bit about a new thorn that I wrote to export data from the Einstein Toolkit to run through SpECTRE's CC code. But first, let's do a little bit of an introduction of why and what I mean by any of that. Oh, right, this doesn't click with iPad. That's okay. All right, so what's the motivation? Why do we care about doing this? Well, we want to obtain accurate waveforms at infinity. Well, why do we even care about that? Fortunately, you already heard Deirdre's talk earlier, which really motivated the why we care about waveforms, why we care about numerical relativity simulations to generate those waveforms. So that pretty much knocks out bullet point 1. Oh, you have to forgive my shaky hands. Despite my best judgment, I had a second cup of coffee. This is the result. It is what it is. But anywho, bullet points 1 and 2, pretty much, Deirdre has already established, kind of 3 and 4 as well. But as a whole, we care about having these waveforms to enable the science that we can do with gravitational wave detectors, and especially we're focused on next generation gravitational wave detectors. Again, existential crises aside. And so as we're preparing for those, one of the challenges is actually getting waveforms at infinity. Because as you gathered, I'm sure, from the Introduction to Einstein Toolkit talk, we perform simulations on finite grids. We can't do an infinite domain, but we are essentially infinitely far away from the gravitational waves sources that we're observing. And so we need some way to get the gravitational waves from finite radius of our simulation out to infinity. And that is a challenging task. And when you're really wanting high precision for these next generation detectors, that's one that we have to address. Again, I keep clicking. All right, so there are a number of different methods that people have used for obtaining waveforms at infinity. One that we do is extract at multiple different radii, and then you can do a fit with an ansatz to see what that should actually be at infinity. There's also methods for extracting at one radius and then applying perturbative corrections essentially to see what that would be at infinity. Some nice equations coming out of our IT for that. And then the other thing is this Cauchy characteristic evolution, where you can extract metric data on world tubes, finite world tubes, and then actually evolve that out to infinity using Cauchy characteristic evolution. Now, I think it's really important here to highlight pit null, which is already a thorn in the Einstein Toolkit and has been for a long time, that does this Cauchy characteristic evolution. And I think it was really the first successful implementation of it, actually. So kudos to them. That's one of the, yeah, you can already go ahead and do that. It's great. All right, and then there's also this new code that came out of SpECTRE, out of the SXS collaboration. So for those of you familiar or not familiar with the SXS collaboration, their previous code SpEC was not open source. Their new code SpECTRE is. And this, as part of that, is their Cauchy characteristic evolution thorn, no, not thorn, module thing, script, software, here we go. And it's because it's separated from their evolution code, the community can use it to then evolve whatever simulations they already ran. And so after talking with a number of the people from SXS, we came up with this idea of wanting to output Einstein Toolkit data into a format where we could then feed it into SpECTRE's CCE. And so that's what I'll be talking about today. All right, so quick introduction kind of into what we mean when we talk about Cauchy characteristic evolution. I'm not going to go in detail into this, mostly because I'm not actually doing the CCE. I'm really just writing an interface. And so go read the paper to actually really understand how this is done mathematically and computationally. But essentially, we're going to first perform our Cauchy evolution in our Einstein Toolkit simulation using 3+1 decomposition that you guys, I'm sure, are familiar with or can listen to other talks to learn more about. But essentially, we're able to solve for our initial data on our initial space-like slice, evolve it through time. And from this, we can then obtain the data on the grid, or we can extract it on finite radius spheres that we can then run through the characteristic evolution. So what you're seeing here in this plot is the pink areas like the Cauchy domain, our finite radius, and then this greenish, tealish bit is the CCE domain, where what we are providing it essentially is this boundary data. Then it sets some initial data. That's where some junk will still come in. We can talk about that later. But we're essentially providing this boundary data, and then it does an evolution that ultimately lets us get what the waveform data will look like at ScRI, which is both spatial and temporal infinity. Yeah.
You have the ability to manipulate a pointer on your screen, because people who are watching this remotely can't see what you're doing with the laser.
Yeah. I am not finding a way to do this. Yeah. Anytime I touch it, it just moves the screen. I'll try to rely less on pointing and more on describing. All right, so now what are some of the benefits? Well, one of the benefits that isn't necessarily specifically a benefit of CCE itself, but rather a benefit of using SpECTRE CCE, is that it also dumps the strain directly instead of dumping psi4 and then us taking the second time integral, though in practice we usually do a fixed frequency integration thing instead of actually doing the time integrals. But essentially, we're able to get strain directly instead of psi4, which is quite helpful. And then the other reason that's really beneficial of using the SpECTRE CCE code is that it helps enable comparisons more. This kind of modularity that we can have can help us directly compare just the evolution without the waveform extraction kind of being part of the equation, because we're using the same waveform extraction method. So that's something Deirdre mentioned earlier briefly about waveform comparisons and code comparisons. And so I think it's nice when we can kind of modularize it and do comparisons differently. Similarly, increased modularity. So depending on what your use case is, I like the idea of kind of being able to plug and play the different pieces of the different codes and really use what's best for any given situation. All right, so brief overview of the thorn itself. It has now been included in the Kruskal release of the Einstein Toolkit. So yeah, thank you guys for letting me get that in. Happy to talk about that process if anybody is more curious. So this thorn is heavily modeled after the multipole thorn, because ultimately what we're wanting to dump, let's look over here on the right, really what SpECTRE CCE wants is these quantities, your metric components and the shift components and the lapse, as well as their radial derivatives and their time derivatives for all of those quantities, decomposed onto, or extracted on finite radius spheres, and then expressed using spherical harmonic decomposition. And that whole extract on a sphere and decompose into spherical harmonics is what multipole does. And so this thorn is very much modeled after that to, not reinvent the wheel. So essentially at each step, that's what it does. It interpolates the metric and these gauge quantities, the shift and the lapse, onto spheres, computes the derivatives that are necessary there, and then decompose it into the spherical harmonics, and then export it directly into the H5 file format that SpECTRE wants. I had a previous version that I presented last year that I was able to feed into SpECTRE CCE, but was requiring a lot of post-processing because I was dumping it directly with the multipole thorn and then post-processing it into the right format and then feeding it to SpECTRE CCE. The really exciting thing about this one is just that it dumps it directly into the format needed, so you can immediately feed it in without the extra steps.
The metric data every single time step at those fixed radii.
Right, it's at every time step, but decomposed into the spherical harmonics on that. So it's not a huge amount of data because when you just have it on the spheres and when you have it decomposed into spherical harmonics, it's a lot like how we do store the waveform data, like as a function of time on finite radius spheres. All right, so just a quick picture of kind of how the parameter file works. For the most part, you really only need this part, which is just you set the number of radii that you want to use, you set what those radii are, and then how often you want it to output that data. Then there's a few other things that you can change, a few other things that are in there mostly just for testing purposes. For most people, it's really just going to be this top section that you're actually going to modify. And then what it outputs is a file, an H5 file for each world tube radius that you specified. And then inside each of those H5 files over here on the right is just the result of an H5 dump so that you can see what the data sets are. And this is how the SpECTRE CCE wants it fed in, is essentially a data set for each of these values. Here you've got all the radial derivatives, all the time derivatives, and all the other components of each of the metric components and the lapse and the shift as a data set. And not super important, this is all detailed on their website if you want to learn more about it. But essentially, it's just the columns of this data set are all of the different multipoles, modes, and then time going vertically. All right. I'm pretty sure I'm going to let you guys out for lunch early, but we'll keep going. I mean, don't worry, I'm not done yet, but I'm just thinking ahead. All right, and so then some brief overview of how you run through SpECTRE CCE. Go to this website or just look up SpECTRE CCE and it's the first thing that comes up for how to actually run it. I think Hector just recently set this up as well, so you can ask him for help setting it up. But essentially you need to install, which is like a tarball that you can download and install on your machine according to those instructions. And then ultimately for each of those world tube radii that you want to use, you're going to run this pre-process CCE world tube file executable that they have over it. And this, it's actually mildly frustrating because there's two different ways that you could feed the metric data into SpECTRE CCE, one of which is the format that I've provided, which is the metric data, the lapse and the shift, decomposed into spherical harmonics. But they have another format that's the Bondi-Sachs variables, and that's what they ultimately want to use. So what this pre-process that they provided actually does is it's twofold. One, it converts the data into that format. But two, something that is quite beneficial, we talked earlier about checkpointing and recovery. And so for anyone who's run an Einstein Toolkit simulation, you usually run it for like 24 hours, and then you resubmit and run it for 24 more hours. So the data is chunked. This pre-process CC world tube script will also take all of that data and combine it. And so we don't have to worry about the fact that our data is, chunked by 24-hour chunks or whatever length of time you run each output for. So it does that. They have a sample YAML file to use, and from my experiences, these default settings have been working great, and all I've had to modify is what my input H5 files are, what output H5 file I want, and what extraction radius I'm using. And then once it finishes running that, which runs very quickly, you can then run the characteristic extract executable over it, which that can take longer. For short simulations, I can do it on the dev queue, or yeah, in like less than 2 hours, or just run it in an interactive dev environment. But for like the plots that I'm going to show you today that uses a D12 or yeah, separation, it takes a little more than 2 hours. So I actually do need to like SBatch submit it. And the only things that I needed to change in there were 2 values called the reduction file name and the boundary data file name. So the boundary data file name is what we're feeding it in, and the reduction file name is what it's outputting it as. All of this is very much detailed on this website, and I'm happy to help, and I guess I've volunteered Hector to be happy to help as well. All right. Now, unfortunately, there is another step of post-processing necessary, because when you get the data out of SpECTRE's CCE, it's kind of in an arbitrary frame, and that can lead to waveforms that, while not wrong, are unintuitive and don't look like you expect them to be. So that's why I called this not in a useful frame. So we need to transform to a different frame. And it's easy enough to transform waveforms between different frames. For this purpose, because it's coming out of SpECTRE and it's in their waveform format, I recommend using their library Scry to do this. I think there's some sample Jupyter notebooks out there. There's decent documentation online for Scry. I'm also happy to help with this. But essentially, you want to map to this thing called the super rest frame. I can point you to papers to read more about it. But essentially, it's a center of mass frame with no instantaneous memory, and with the angular momentum in the plus z direction. And converting to that frame makes your waveforms look like you expect your waveforms to look. Again, with the clicking. Right, I already said some of this. Use the Scry package. Look, I point to the tutorial. I know that's not super useful because you can't click it. But if you just look up the Scry documentation, it's there. But essentially, you create an object. It's in Python. It's a Python library. So you create an object that's the asymptotic bond d data. They call it just the ABD. And then you compute what transformation is necessary to convert it into the super rest frame. And then you apply that transformation, and then you're good. I will talk more about this later. I have a little section that I call systematics. But one of the tricky things is when you compute this transform, it's computing that on a certain period of time, because like the super rest frame for the in-spiral or the merger or the ring down are not all the same. And so you have to provide it some reference time and padding. And there's a little bit of finesse necessary there. All right, so now let's look at the results. Let's see what we get. Okay, so this is just an equal mass non-spinning simulation. It had separation 12. This is just the plus polarization of the strain in a face-on inclination. So it's mostly dominated by the 2-2 mode. This is, at least in my mind, if I just picture a waveform, this is the waveform that I see. But where it gets interesting is now let's look at an edge-on inclination. And suddenly we see this thing that we don't usually get, which is the memory effect. So this is something that I expect most of you have heard of, but maybe not everybody. We often think of just the oscillating waveform that then comes back to 0. But at least in certain orientations, when the 2-0 mode is particularly apparent, what you actually get is an offset, where the final state of the waveform is different than the initial one. You actually are left with some sort of offset. And so this is it looks like such a small thing to be excited about, but this is a really exciting thing to actually be able to get out of our waveforms now. And there were a few reasons why this was tricky before. So one, it can get lost in the extrapolating to infinity if you're not doing an actual evolution. And two, it gets lost when you're integrating from psi4 to obtain strain. And so now with getting strain directly and evolving out to infinity, we're able to see the memory effect. Okay, so now we're going to do some comparisons with other extrapolation methods. Yeah, okay. So now we're just looking at the amplitude of the 2-2 mode for some simple comparisons here. So what you're seeing in the differing shades of blue is different finite radius waveforms. And you can see how they all kind of, so I've aligned them all to peak at 0. But you can see that they're all kind of trending towards something. And then in pink is what I'm calling the perturbative method. This is the method I described earlier where you can take one finite radius waveform and extrapolate it to infinity by applying these corrections. And then in black is what I get after feeding it through the SpECTRE CCE waveform or code. And in both the perturbative and the SpECTRE CCE case in this simulation, I'm using the r = 100 radius as my initial world tube radius. But what's great is you see pretty solid agreement. The perturbative definitely looks slightly different than the SpECTRE CCE evolution, but at least qualitatively, they align pretty close. All right, and then I really do want to highlight how awesome Pitnell is. And so I'm doing a comparison here. Here I'm doing it directly on psi4 because I didn't want to contaminate things by doing the time integration to get strain. Though Pitnell also dumps the news actually, so which is basically the time integration between strain and psi4. But anywho, so I went straight with psi4 here, and what I'm showing is a comparison between the Pitnell CCE and the SpECTRE CCE. And I mean, here zoomed out, you can see that it looks perfect. Zoomed in, it's nearly identical. So great sanity check. And yeah, good news for both of them. All right, and then some comparisons with SXS waveforms directly. And so now, once again, I'm still showing those finite radius waveforms, and the black is still the waveform obtained by running an ETK waveform through SpECTRE's CCE code. And then SXS here, the pink, is a SXS waveform that has also been run through their CCE. Equal mass, non-spinning. It's a much larger separation than this simulation, but I was flabbergasted, to be honest, to see just how well that aligned. So I've not yet had the chance to compute mismatches. I was hoping to get that done this week, but alas. But I mean, you can't see the pink, so I'm thrilled. This next one looks like less agreement, but after looking at my data, or like while I was preparing these slides but didn't have time to do an analysis, I think this is just that they're in a slightly different frame. So this is specifically the 2-0 mode, and this is what's called the memory mode. And so you can see kind of how when you combine this with the 2-2, you get that waveform I showed you earlier that looks like it's going up. What I had done here was just I shifted the SXS waveform to line up with the ETK waveform because theirs was a much longer simulation. And so it had accumulated memory before the Einstein Toolkit one started. And so I just shifted it. But when I was making the slide and I was defining the super rest frame, and I noticed that it said where the instantaneous memory is 0, I realized I think what I actually needed to do here was when I transformed the frames of these two waveforms, make sure that they were in the same frame at the same time. I think that would fix this. But just aligning them, it's shocking how good at merger that did. All right, and then a brief mention of systematics. So I mentioned how you need, and I just talked about it again, actually, how you have to kind of fine tune T0 and padding time to produce a clean waveform in a useful frame. So based on their guidance on the ScRI documentation, the padding time should be roughly 2 orbital periods, and T0 should be set such that T0 minus padding time is after junk. Because apparently, or essentially, T0 is the center of your window, and then it goes T0 minus padding time, T0 plus padding time, and that's what it does the transformation over. So you want that to be after junk, and I guess a total of 4 orbital periods essentially for that whole window. And this can require some careful fine tuning. Otherwise you get wiggles in the data. And so I wanted to show you what those wiggles look like. So on the left, I just have what I called bad fine tuning of T0 and padding time. And it's producing a lot of wiggles throughout here. And you can kind of see where it flattens. I realize now that this is not super informative because this being 500 was before I shifted this for this to be the peak. But roughly this 500 was in the middle of this bit that seemed flat because it was essentially computing the transform over this tiny little bit. And so the rest wasn't quite as good. Over here, well, you can't see it, but it's got a padding time of like 800. And it's got a time here. And so it's in the right frame all the way through merger and for most of the in-spiral. Now, what you will note, if you were keen-eyed, is that all my previous plots, I started at -1000. So I had cut off all of this before here. Because you can definitely still see that there's wiggles here. So part of that may still be fine-tuning these padding times and stuff, but part of it also may be junk from the CCE evolution itself. This is something that SpECTRE or SXS faces as well with their waveforms, is that I mentioned that we're providing the boundary data, but they do start with some initial guess, essentially, on the initial time slice. And right now, it's not a very sophisticated guess. And so they're working on improving that. What they do with their waveforms, since they are just so long, is they just cut off the first 1,000 or 2,000 M and are just like, yay, we're good. The wiggles are gone. Not grand for us to do that because our waveforms aren't as long, so it's not as great to cut them off. But I was pleasantly surprised that I was able to still have a pretty solid waveform, even cutting that off. So there may still be some work to be done there. But the point to take away from this, if you are using this, is that if your waveform comes out looking like this, you just need to fine tune these values. And if you have wiggles at the beginning, yeah, that's still a work in progress to try to solve. And that's kind of just what we're dealing with. All right, and so then this plot is showing another kind of aspect of systematics, which is that I mentioned how you take a finite radius world tube and then feed it out or evolve it out to infinity with SpECTRE CCE, but you could do that with multiple different initial world tube radii. And so here I'm showing the results of feeding it all the way through CCE, but if you started with different world tube radii. And you can see decent agreement, but not perfect agreement here. This is one of my less polished plots. It was one of the most recent things that I've done, so I'm still working on it right now because for this one, I was using the same window, that T0 and padding time, for all of them. And you can definitely see that some of these still have some solid wiggles. So that might be inevitable. It might be that in my initial Cauchy evolution, some of those higher radii maybe aren't well enough resolved to really use for this purpose. And so I want to look into that because that's kind of the challenge, right? Since we're trying to get something to infinity, you want to start with something pretty far out, but you also need to make sure that it's resolved enough out there. This is also all done with a Cartesian grid. I want to try using this with llama and stuff so that I can see what I can really do out there. But yeah, so this needs a little more looking into, but yeah, because you've still got these wiggles here. So might need to be fine-tuned between each one, or it might be that some of those radii aren't well enough resolved. All right, so this was a half-hour talk, not an hour-long talk, but I'm not just going to sit up here talking unnecessarily to you guys when lunch awaits. So let's wrap up. Obtaining waveforms at infinity is a challenge, but it's important, and it's something that we're really going to need to be able to do with high accuracy as we prepare for next generation detectors, especially, and even O5, to be honest. There are several methods that exist, including several ways of doing extrapolation or doing CCE with Pitnell. This is just another approach that is very useful. So we can use the CCE export thorn to dump the data into the format that you need, and then you can feed it through SpECTRE CCE, and then you can fix the frame. And what's really exciting is that this produces waveforms with memory due to the method of evolving out to infinity, combined with the fact that it's directly computing strain instead of integrating to obtain it. And then we also showed that it's quite consistent with the other extrapolation methods, including great agreement with Pitnell as well, and with SXS waveforms themselves. All right, happy to take any questions. Yeah.
What's the CCE of it?
Anywhere between like 30 minutes to a few hours on the waveforms of the length that we're using. For like my D12, it was like on order 2 hours. Yeah.
So, I have sort of a little example from where you said output every 128. How often do you need to output?
That is something I need to. That is a thing I need to add to the systematic study for this paper that's in progress, because I haven't really looked into that yet. I haven't done a comparison. I defaulted to those numbers that we often would output our waveforms at, but I haven't.
Asking the question be repeated.
Oh, sorry. Yeah. So sorry, brain just completely. Right. So I had it set, I showed an example par file where it was set to output every 128 iterations. And Peter was asking if I've looked into how often we actually do need to output it in order to get accurate waveforms. And I was saying I have not yet looked into that. That's on the to-do list for the systematic section. Ideally, the less you output it, that's great, because then it takes less time to feed it through CCE for one thing, and it is dumping less data. But haven't actually done that analysis yet.
Related question, do you know if it supports outputting at uneven time intervals, or do you have to have the same delta T for all there?
Repeat the question.
Let me clarify the question. Do you mean like for all the different radii, or?
The time you output the CC data, does that have to be at regular time intervals, or can it be different time?
Oh.
Different delta T for different things.
Gotcha. Peter was asking about the delta T for the different waveforms and if that has to be consistent. I mean, in my thorn right now, it's just a fixed every 120 or every if it is that iteration, then it dumps the data. In terms of actually feeding it into CCE, I'm not sure if they require it to be on like a regular time interval or not. I mean, when you feed it in, the first column of the data is the time. So in that sense, it's not just assuming a fixed time step. So I wouldn't be surprised if it can handle varying time steps. I've never tried. What's? What's the question online? Okay, here, yeah. Who has a question online? I can't really tell.
That would be me. Kind of a similar question. I think you have got a question. How long does it take to post-process the data once you have it? do you see any impact on the speed that you get from having to write out the data, or is it negligible?
Yeah, good questions. I guess I don't need to repeat those. Everybody heard that. Yeah, okay. The running it through, so the frame fixing can definitely take some time. But so one thing that it does, in Scry, you can compute the BMS frame transformation on, like you can downsample before you compute the transformation and then apply it to the fully sampled waveform, which I would highly recommend doing, because if you don't downsample, it does take a long while. But yeah, the post-processing and the frame fixing is actually, I mean, it's short compared to actually doing the CCE, but it definitely takes minutes. When I ran it over the actual SXS waveform, which was really long, it took me that would run for 20 minutes to an hour. I don't remember. I'd usually set it and then leave because it would actually take a while. But it definitely depends on how much you downsample. There's a chance I could have downsampled more and wasn't sure. And then in terms of the dumping the data or running CCE export, I don't think I'm seeing it slow down your simulation much. I have not actually benchmarked that to test, but I don't think it's slowing it down too much because it's not too computationally intensive. I mean, if you try to output it every iteration, it slows your simulation down a ton. I did that accidentally once and was like, why is this running so slow? But yeah, when you do it every 128 or something, it's not bad. And then you had a question?
Yeah, hi, this is Bill. So I guess I have two questions. One is, you made plots where they overlap very nicely. By the way, great talk. But have you done residuals, and what kind of residual would you expect? And then the second question is, the super rest frame is all new to me, and it looked like you're having trouble picking the right one, or it's having trouble. So how hard is it to get that super rest frame to agree with my detector frame, I guess is the question. So.
Yeah, so I haven't actually computed residuals yet. So far for this talk, I just managed to basically get the plots overlaying them together. But I want to compute residuals and I want to compute mismatches. I will say some of these, the visual agreement was much more than I expected, to be honest, which was really exciting. I'm hoping that this greatly improves our mismatches with the SXS waveforms. Which are already good. We already have strong agreement, but I'm hoping this makes it even better. And then I think the frames aren't, they're just nuanced and tricky because some of it kind of changes throughout the evolution depending on how you're defining it. So in terms of getting that into the detector frame, well, a lot of that PyCBC, for example, can kind of do for you if you provide it in the NR frame and in the super rest frame as well. So a lot of that logic, I don't think we have to do ourselves for the most part.
Okay, thank you.
Okay, and then the in-person question.
Perfect. So it's how do you do the radio and leave on the spheres?
Oh yeah, the question was about computing the radial and time derivatives on the spheres. So one of the nice things about Carpet is there's a interpolator. The interpolator that can feed in the points on the sphere can also give me derivatives, coordinate derivatives in the XYZ direction. And so I just had that interpolator give me those as well. And then it's just math to convert from XYZ derivatives to radial derivatives. And then the time derivative, this is actually an important thing, so I'm glad you asked that. The time derivative of the lapse and the shift are something that are specified in ADM base as grid variables, but not every evolution thorn writes back to them. And so right now, this definitely relies on whatever evolution thorn you're using, writing back the time derivative of the lapse and shift. And then the time derivative of the metric is computed from the extrinsic curvature. Okay. Oh, yep.
So you mentioned that the padding time would have to start after jump has passed, but that would be the CC process with the CC export thorn itself. Like when you store these data, you just start from the simulation, or do you also have to cut out the jump?
So the question was about cutting out or I mentioned that the padding needed to start after the jump time, and was asking about if that's taken into account when outputting the CCE data and stuff. So the outputting of the CCE data is, or like that I'm dumping in to feed into CCE, that I'm outputting all of it, just like from the start of the simulation. I'm also feeding all of that into SpECTRE CCE. This is only in the post-processing that I just make sure that those first like 150, well, like 75 m plus whatever your extraction radius is, just the padding time value, and T naught just needs to be after that. It doesn't really affect the rest of the process. It's just when you're actually analyzing the waveform. Not too different than when we just cut off junk before we, feed into LIGO and things like that. Yeah.
Say you're looking at like the 2-2 mode, right? What like a waveform. Do you just need to extract the 2-2 mode of the metric components, or do you need like everything?
No. The question, yeah. Thanks. The question was, if you're looking at just the 2-2 mode of a waveform, for example, do you only need to output the 2-2 mode of the metric components and things like that? No, you need to evolve all of it out to infinity. Right now, I think I'm trying to remember what L mode I'm outputting up to. It might be L equals 8. Though I don't know that all of those modes are necessarily super reliable, but no, you need to evolve all of it in order to actually then compute it. It's also a key thing to note there is when we're talking about waveforms like that, we're usually using spin-weighted spherical harmonics. Whereas in this case, this data is being dumped using just the scalar spherical harmonics, so spin weight 0. So those aren't actually even equivalent modes. Yeah.
One more.
Yeah.
So in all your examples here, you show like a black hole mergers where you have merger and bring down.
Yeah.
The signal is zero at the end. Does any of this rely on that? Do you actually have to have a signal zero signal at the end of? Would it also work if you, for example, had a black neutron star merger where you still have that bringing of the central objects?
The question was about, the examples that I've used have done binary black hole simulations where the signal is 0 at the end, though I guess except memory. And so the question was whether this would, if anything relies upon that, or whether it would still work for things like, for example, neutron star, where you might have a neutron star at the end. I don't immediately know of anything that would keep that from working. I'm not well enough versed in the way that the actual CCE is happening on SpECTRE side to say that with any sort of certainty. But I don't immediately know of anything that would prevent that. Okay. Well, great. Then I think if there's no more questions, we can, I think, wrap it up for lunch.
Let's thank the speaker again.